You have the camera on?
Yeah.
You got the audio on?
Yeah, I received it.
All right, we do a little sound check here. Okay. Finally, we got the projector on. Can we? Stefan, you okay with being recorded? You're a rockstar.
Yeah.
Rockstar's not being recorded. All right. So, can you just sort of minimize it a little bit so we can see if the video is on and what they're actually seeing? Okay. All right. So. Okay, we're in presentation mode. Just let me just do some housekeeping. We'll get the first speaker on. Thank you for your patience, everyone. The turnout here today, despite the Delta variant. I recognize that there's some Delta hesitancy now. There used to be vaccine hesitancy, and now there's whatever it is. It's a lovely day in New York. We had a thunderstorm. I was afraid that we were going to get rained out, but no, the clouds have parted, and the gods are smiling upon us. So it's just wonderful to see all of you. People, glad to be alive myself. Just about a year ago, a little more than that, March 11th, I remember that was our last live event, and that was the day the WHO announcement came. We decided to push through with the event nonetheless. It was a small crowd, and we had the gentleman from NYU who was talking about hedge funds from Tendon. Leon might know him, of course. We went for dinner, if I may digress, and we went across the street to Tecumseh, and we were joking this could be the Last Supper. So I said, listen, guys, just eat up, drink up. Who knows if I'll see you alive and what happens. So we're kind of in the same mood here tonight that, it's time to eat up and drink up because we're still alive. So that's cause enough. It's fantastic back, and it's also wonderful to have so many of you there remotely. Thank you for your patience. I'm sorry that the Francis Tavern was, they've been around for a couple of 100 years, so it takes them a while to get extra working. I gave them 2 months notice. But it's a very historic spot. For those of you who don't know, this is the oldest bar in New York. It's where they hang out. The room next to us, the long room, that's the farewell speech was delivered. And we have other speeches here tonight. But before that, I want to thank my team because without them, all this wouldn't work. And we have some people remote as well. We've got Krishna in Miami. We've got Gautam Wahi in transit. I think he might be on the subway or lost in transit as we speak. But the MC for tonight, Yuan Hao Feng. Please come on up, Yuan Hao, so people online can see you. He's the guy running the show online.
Yeah, thank you, guys.
Yuan Hao is in the Rutgers. He's a quant in the MFE program. I think he's on the market, right?
Yeah.
Okay, so if you need a smart guy, there's Yuan Hao. Thank you. We've got a couple of our other guys. Sonny, you want to say hello? I don't know if people can see you from back there. Sonny just at AQR, so he's off the market. And he's been interning with us. Great guy, smart guy. And we've got who do I see over there? Isaac Liu, the man of the moment. Thank you, Isaac. For making it happen. I think he's interning at Deutsche Bank, but you may still be on the market. So if there's a higher bidder, we'll find out. And what else? I don't see any other team members, which means I'm pass it on to the speaker. Well, thank you for showing. Well, thank you for showing up. That's no fun, but no, I mean, look, it's a small community, and we're a friendly crowd, so it's lovely to see Professor Leon. I can never pronounce your name right. Tadavos, and hopefully his brother is logged in online. We got Paul Martin all the way from California. Glad you moved to New York. And of course, we got our friend from Citigroup, and from I see Rudy back there, and we got a professor from Villanova, good old Dan Hupsher. Thank you for coming, Dan. Gilbert, and we've got some new members, Guru and Ankit. Thank you. All right, excellent. So. Without further ado, we've got a speaker with that. I met him actually at a NASDAQ TV, some kind of event a couple of years back. Stefan Jansen?
Yeah.
Jansen? Okay.
That's how they do it back home.
Never quite sure.
So many variations.
I work for Deutsche Bank, but not hard enough. I'm assuming that's German, or is that Canadian? Okay. All right, perfect. So, Jansen's, Stefan's got a very impressive resume. It was so long I couldn't memorize it, but I remember some Harvard, Georgia Tech, and Berlin.
Yes, that's where it all started.
So he's got a lot of degrees. More importantly, he's written a book. That's why we're here, the book. So we're going to talk about his book, or at least one chapter from the book. And without further ado, very impressive guy, knows a lot about everything I don't know. So Stefan Jansen, thank you.
Awesome, thank you. So exciting. So I wonder, how do we do that with the slide? Should I be clicking on something, or?
Yeah, maybe.
How's he going to click?
Yeah, maybe I'll stay here.
Okay, why don't you pull up a chair and then we'll make it a team effort.
You guys just keep. I can just talk about life while we look at about the last year. Very cool. So I guess we're all pretty excited. Life in person. Who would have thought?
Everybody needs a drink. I feel like the speaker needs a drink.
Please.
You can't be a
I take a beer. I take a beer.
All right. Yeah.
Pilsner or something of that nature. Yeah, very cool. That's when Millen sent the email about the event and it said in person. It probably should have gone in the spam folder, right? Because, that's a red flag these days. But here we are. So what do I want to do? I want to talk a little bit about deep learning. It has evolved over the last few years, and that is related to the book that Millen just mentioned. So maybe we move to the next slide where we show the agenda. So what I want to talk about today is just briefly, why am I here? Where does the book come from, and what does it actually talk about, and why could that be interesting to you? And then how deep learning for asset pricing has evolved since we published the book, and what also might be in a third edition that is planned for the end of this year. So the main thing is really that the deep learning approach has sort of a think idea where you just throw everything you have at the model and hope that it predicts something useful, to actually imposing more economic structure based on what we know how returns potentially are formed by risk exposures. So we'll see a few models and also some criticism of these models. So kind of the outline. So let's move on to the slide. So this is a picture of the book, and it's called Machine Learning for Algorithmic Trading. You may have come across it. It's been out for a year already, and it's the first edition came out at the end of 2018, I think. So it's been a while. It's comprehensive with 800 pages. And most importantly, there is a very packed GitHub repository with it, where you have 150 notebooks that show all ways of using machine learning to predict returns, or how to build optimal portfolio, and to many other things. And the 4 parts that in the book, they cover sort of the basics, how you work with data. It's of course all Python based, how you not only get the data, prepare them, maybe extract useful information through feature engineering, and some background on how markets work and how portfolios are optimized. Many of these things for you probably are fairly straightforward. And then we jump into machine learning, and then there's a large part that basically covers a lot of the relevant models, from the basics, linear regression, probably know from your MFE programs, to the constrained versions or the penalized regressions, all the way to gradient boosting. Then that talks about natural language processing, one of the areas that, of course, holds a lot of promise in finance, and we show how you can actually extract features. And then lastly, there's a part that covers deep learning, and it goes from the basics again, vanilla neural networks, and recurrent neural networks, convolutional neural networks, to autoencoders, that's what I'm going to talk about today, and also includes a chapter on generative adversarial networks that you can use to generate synthetic data, which is a very dynamic area of research right now. And then there's a part that talks about reinforcement learning. So one more step ahead to the next one. So the main goal of the book, which is very hands-on and practical in nature, is to really resources that you can use to start get your own experiments going, right? So there's a lot of free code examples that have become fairly popular. So the repo has over 4,000 stars, which is quite a bit for a book repo that's not a software application. And it was actually among the top 10 most popular GitHub repos for occasionally. There's a lot of repos. So that's great. And available, and you see the address there. And a website for the book and ML for trading that also comes with the community. So if you decide to experiment with things in the book, then there's a few hundred on there now to actually implement and learn from each other. So that's that. And with the book also comes now support for some of the key open source libraries, especially Zipline. Many of you may have come across Quantopian. Open source Zipline is a backtesting engine. Unfortunately, I had to close doors at some point last year, and Zipline hadn't been updated in quite a while, which was a bit of a hassle because you had to work with old Python versions. So we updated those, so you can now use Python 3.8 and 9, and all the sort of most recent versions of the analytical libraries, pandas and what have you. And also the other support libraries like AlphaLens and PyFolio, they're also now available with updated documentation. And again, so that you can bring your own data, and we hope to really develop Zipline further once we relax a bit over the summer, because the third edition will use a broader variety of data sets than what we've done so far.
So if I may interject, Zipline was part of Quantopian?
Yeah, I don't know if it existed actually prior, and they just took it and used it as the engine, but they've been developing it for the past. And it also was the engine online that powered the entire platform.
Somebody else bought out the remnants of Quantopian, right? I thought that's it or something. Oh, Robin,
yeah, they're sort of acqui-hired, I think. So I don't think it was a full-on acquisition of the company, even though they may have the rights. The motivation, I think, was to get the team. But who knows? Maybe they do something with the software as well. But for instance, the Zipline documentation, the whole website went stale, so it doesn't look like there's a lot of engagement there. Yes. So I've started a little bit. So it was quite a bit of push to kind of get this to where it is right now. If you're interested, it's open source. We're always looking for contributors. There's a few, and I think we'll be doing more come like the end of August going forward. Because the main concern, if you work with Zipline, you might know that ingesting data is a little tricky. There's a somewhat rigid framework around that. But it doesn't look like it's going to be too difficult to open that up. So that you can either use just a database approach where you define results with a configuration file or something of that nature, and then you basically work with a broad variety of inputs that just style or high, low, close, and so forth. So that's the plan. Good. Yeah. Question time, right? But now on to the day. So we're going to bring to the oldest bar in New York, the newest in deep learning, especially with respect to asset pricing, right? So as a disclaimer, first of all, deep learning in finance and generally, of course, has a bunch of different use cases, right? You've all heard about alternative data, so that is kind of where deep learning game, right, when it comes to images and text data. Question is, does that also work with standard financial data where we're talking returns and the like? And these are familiar points, so I'm just warming this up a little bit, that while there's a lot of excitement around deep learning, just as machine learning in general, reasons to be skeptical whether that might work. And on the pro side, of course, well, we like to predict returns, and deep learning seems to be really good at that. So why use it? And of course, we have a lot of potential, and deep learning is really great at high-dimensional data. So that's also a good reason. And all these complex relationships, kind of speaks in favor of deep learning. And again, we have potentially alternative data. So there's a lot of reasons, of course, that make people excited about this. But then on the other side, you have the experience that deep learning works really well when you have a lot of data where you actually have plenty of signal, like recognizing cats on images. So finance, short history, very low signal ratio, especially when it comes to returns, given the market nature the data originated from. And then you have changing markets, and you also have the issue of interpretability, right? So sometimes you actually have to answer the questions, what needle one way or another in your model, and you can just put out the black box and have it answer the question. So there are some reasons why people are skeptical. So what has happened? Let's take a look at the next one. So I want to summarize 5 papers that are partly reflect what's in the book, and they are actually in the book, and then some newer things that reflect sort of how the discussion has evolved since, and also what might be part of a third edition. And so, as I said, and I think finance came a little late to machine learning, because finance, in my observation, has a very long history of doing quantitative research. So it's like we kind of know already how this works, right? But whereas like in other fields, like deep learning was really successful in images in 2013, 14, with the big competitions that the deep convolutional neural net won for the first time. And it took a few years for finance to adopt that. And then you had the folks that were like super bullish, and the others that were, completely opposed to this ever being successful. So what happened? So there are 5 big papers, as I said. The first one called Empirical Asset Pricing by Gu and Kelly, affiliated with and Hugh, affiliated with AQR and Yale, that sort of opened the box and took this kitchen sink approach, comparing a lot of different models and using a lot of predictor variables to really predict raw returns or set returns. And that introduced a lot of the discussion and methodology to the field. Others, but that's kind of a very popular example. 500 citations by now in the Review of Financial Studies. Then similar authors, so a bit of overlap, came up with a next two are closely related. This characteristic variances and the autoencoder asset pricing models. The second sort of generalizes the first. Took a new approach, and I'll talk about this in more detail because that's actually replicated in the book. So one of the interesting aspects of the book, I think, is that it not only covers sort of the basics, but it really implements research that is literally just being published. It takes an approach, this paper, by really trying to encapsulate and model sort of more structure, that we know from the theory of asset pricing and the like, to incorporate equilibrium conditions and others that are not present in these sort of more brute force or kitchen sink prediction approaches. And then there's an interesting, slightly newer one by Chen, Pager, and Zhu. They're from Stanford. Chen is now at Sigma, has been there for a few years. Pager still at Stanford. And there's a newer one still by Avramov that criticizes some of the other four and why they might be difficult to implement in practice. So that's what I'm going to talk about. So let's see the first one. Next slide. Thank you. So the paper Empirical Asset Pricing via Machine Learning, implements basically a horse race from simple, ordinarily square regression way to somewhat deep neural networks. In that case, they use neural networks up to 5 layers deep. Each network layer has something like 32 units or so. One has to say that compared to how deep learning is typically looked at, on how one is familiar with that from other domains, these are models. You may have come across this GPT-3 model. It's like a text generation model produced by OpenAI that has over 100 billion parameters. Comparatively small. But they use basically a model to, and you see the little formula there, where we want to basically model, the expected return using a bunch of different features and comparing a lot of different models. So they use 920 different variables that, it grows that way because there's a lot of interactions between macro features and asset prices or asset characteristics and so this paper reflects a lot of what is in the book. So the book focuses across different chapters on introducing how different methodologies or models or machine learning algorithms work, and then applies it to some sort of return prediction exercise, and then analyzes how you could actually backtest how a strategy could utilize the results of such a model. So could you actually implement, say, a long-short strategy, using the decile sorted predictions. So that's what this paper does, and it was very helpful because for the first time, I think, in finance, it really laid out cleanly how this all worked and how this could be applied to a financial data set. And then a lot of different tests, familiar from traditional asset pricing, which the predictions really explain variations in return, and then also analyzes the profitability of a strategy that the ranked based on predictions. So on the next slide, if you have any questions, time. So here's some.
Sorry to interrupt. By the way, you're
Thank you.
we encourage it. If something's not working or people are
Yes. Everybody logged out already.
Sorry.
Good. No. That was very welcome. Okay, cool. So in this case, you see that the best performing model, and they also the performance of the predictions across different subsets of assets by size, right? Because one of the criticism or the potential suspicions was that maybe you're really good on predicting those stocks that are very hard to trade. Which means maybe it's not really implementable after all. So they compare how the models fare across all stocks and then for large or for small stocks. And you see that overall, the green one is the top 1,000, some of the largest stocks. But also you have most data is where the neural network outperforms, but really only slightly. Random forest in this case. Boosting is pretty competitive with random forest, so in that case, it had a little bit of an edge. But the differences also are not massive, right? So one also has to put in perspective that while it is better and makes better use of the information, apparently, these are not revolutionary gains. So that's one aspect, right? So in this case, we have one of the first times evidence that in terms of return predictions, we got outperformance of the neural network, albeit a smaller, a shallow one, and not like a home run necessarily. So that's number one. And then on the next slide.
Yeah, but before we move on, so I apologize. What do we, can you just go, yes, thank you. Monthly outsample, so you're plotting the R squared,
Okay,
R squared.
Good. Yeah, I went a little quickly. So the idea is to look at how does the model's prediction, how much of the return variation do the model predictions explain? And these are monthly data, so that's why it's monthly variation. And it's out of sample in the sense that the model is estimated beforehand and then implemented on test data.
But these are not, you're not looking at typical return spread or something, or backtesting the efficacy of the ICs and returns. So this is maybe you're talking about R squared or what? I'm not sure what you're.
Returns, and you have returns, right? And then you can compare how much of the variation that you see on in the returns that you observe, how much of that variation the model actually captures.
Oh, okay. So this is, would you say it's more kind of?
Yeah, they try to use the traditional effective model of evaluation metrics. They use others as well, but they want to embed this discussion of with familiar models, as most of the other models do as well. So they use it. They look at time series, R squared, sectional R squared, and then they also look at the profitability of the strategy that uses looks at the predictions and then goes long the top decile and short there.
You also mentioned top and bottom. They say, well, so the whole is the whole cross section, and then you've got separate.
Smallest and largest stocks by market cap. So that was the point where maybe the predictions really performed well just for the small stocks where there's less information efficiency, but unfortunately we can't really trade on it because it's too costly, and so it's a nice demonstration, but that's it. So.
That makes sense. I think for R squared, probably makes sense that you see better results in the largest stocks as opposed to from a return standpoint. If you were doing, outsample that T cost, you'd probably see much better results in the smaller names.
Yeah. So if you look at the next slide, and so that's one of the criticisms for the next slide looks at the Sharpe ratios of this decile-based long-short portfolios. Again, you have a neural network doing best, but here they actually do not differentiate any longer between asset sizes or between market cap groupings. And I later go to this Avramov paper, and they criticize precisely that. So they reviewed this paper and the others, and they sort of removed from the data set certain stocks, either small ones or stocks that were distressed or things that for other reasons, might be difficult to trade. And then they always find that a lot, like some 50% of the gains disappear. Right. So So in that case, we don't have that breakdown for this paper, but obviously. So, but at least in this context, you see that the neural network does achieve the highest Sharpe ratio, which is.
So what's the underlying model? Are you trying to use fundamental data to predict classifiers?
Yeah. So if you go back like 2 slides. So what the model does is it uses 920 input variables. It uses the standard characteristics that you've seen in all the different factor zoo papers. It uses some variables, and then it interacts those. That's why we get so many features, and they're industry dummies. So it's a fairly large, and that's why the ordinarily square model completely takes. But as soon as you start using regularization to kind of squeeze out uninformed coefficients, you start getting better results. And it's a relatively short panel, because even though they use a lot of stocks, like 30,000 total stocks, I think with an average like 6,000 stocks, so it's unbalanced. It's monthly data, right? So even though it's
It's all US, right?
It's all US. The standard problem.
Okay. So this is data.
So
nothing fancy about news or
the like. So it's literally very standard asset pricing, anomaly type of discussion, momentum, proxies for momentum. So it's basically your the size, the profitability, momentum, and then proxies for those. Which is also why they find that it's really only 10 of these variables that really matter, that explain like 99% of the forecasting variation.
Yeah, that would be very interesting because we've run our own factor zoo on over 600 plus factors, and it always comes down to actually a very tiny number.
Yeah.
Although what that small number of principal components is kind of
yeah. You see the later models actually they utilize very much this fact, right? So this model goes the opposite way. So let's throw in everything. That's why I call it like the kitchen sink approach. And it's interesting because the idea is all these neural networks that can digest all this, but you still need, that means you have a lot of parameters you need to estimate, right? And with little signal, that's a tough task. So the more modern models, they actually impose structure so that there are fewer parameters, and then they end up with something very similar, like dimensionality reduction, fewer factors that are more meaningful.
But those are still all linear, right? Like, here I think even with an NN3, you might be picking up some nonlinearity. You might be picking up like, root size or whatever, like, something that's not, unless somebody starts with a variable called the square root of.
Neural networks are able to work to discover nonlinearities, interactions, and the like in the features because the activation functions are nonlinear. If you had a neural network where each activation function it would just you put through what comes in, you gain very little because you have these activations, the rectified linear unit. That is like a call option. You get.
Is that the one you use?
Yeah.
Or
Yes.
Something else?
The ReLU activation is mostly standard in neural networks because it's fast, right? It computes very quickly because obviously like even models have a lot of you want them to less complicated. But yes.
So are you using like a CMRNN which has memory or using like CNN?
This one?
Yeah.
So just to be clear, this is not my model, right? I'm using a very similar model in the book, but this is a research paper. But this is a vanilla feed-forward neural network. So there's nothing fancy about it, right? It's like, so I didn't go into detail about how it works, right? But they apply like basic regularization techniques, right? So there's a little bit of, I don't think they, this one actually was like the other papers use, which is very popular, like you have randomly units dropping out during training so that, you have to build some redundancy in. But they use, I think, L2 regularization for the units, and in some cases they use ensembles, so they have multiple models and then average the results. So there's some tricks in there to kind of try to work against the excessive variance of the results. So the models definitely gains compared to linear regression and regularized linear regression contribute to the fact that they pick up nonlinearities mostly, and make more efficient use of the information they have.
And you're getting this data directly from the authors from the study that you're replicating, or you get?
So other authors actually have published, which I'm getting to later. They actually have. So in the book, I'm using different data. I'm using actually daily frequency from Quantopian had like the 3,000 stops in the history. So because the book has to have data that is publicly available, right? So the Quantopian data mostly it uses some Stoop data, Japanese ETFs and things like that, and it uses minute data from AlgoSeek. So I have like an industry partner, so they provided a free sample of minute data with some machine learning feature of like order book characteristic, like bid-ask kind of features. But I'm not using this data set, which is from CRSP. But one of the other authors on their website, they actually published the data. They're sort of anonymized in the sense that the ticker names aren't there, but you have all the characteristics. So you have the returns, you have the asset characteristics, and you have the macro features. In their case, it's a lot, which basically allows you to replicate all these papers, using and then you can actually properly compare them because, except for the 3 Kelly data, the 3 Kelly papers, they all have very similar data sets. But
is that a field risk? If you anonymize it, they'll let you use it for free?
For now, it's all.
Okay.
Maybe. So I'm talking to Sierra.
Useful things you learn in coffee. You want a free copy of Chris.
So yeah, it's useful.
I have a question.
Yes, please.
So maybe you're getting to this, but what's the time horizon on this prediction?
A month.
A month? So you're predicting a price 1 month in advance.
So in that case, the idea is that an institutional investor might typically, rebalance once a month. So that's like a relevant time horizon. I don't think that's universally applicable, but there's certainly use cases for that. So again, in the book, I usually use mostly daily frequency, at which horizon it's obviously a little more complicated, and you have less of these characteristics they're less useful because they change much less frequently. They're often like they're often yearly, quarterly, or monthly variables. These features, these 94 characteristics, they're like slow-moving variables. Which is also why if you rely on this type of data, it makes sense to look at longer horizons. Good. Lots of stuff to go through, so let's see if we get there. Okay, so these were the portfolio results, right? So as the baseline was established with this paper, which again reflects many of the examples in the book, which is let's just predict excess returns and then form portfolios based on the predictions and works, and to some extent, that's all before transaction costs and all other concerns that maybe the assets you have in this may. So, right, so there seems to be some value in this. Clearly, if we look at the we can demonstrate that machine learning or even deep learning in a modest scale help.
I would see what actually utilizing your life.
But then
how returns would allow us to impose which in turn would allow us to use field parameters and maybe make more efficient use of the information and also circumvent the whole noise
problem. So let's look at the next model that does that. So there were 2 published, 5-6 months after the other by almost the same authors around Brian Kelly from Yale and AQR. The first one was called Characteristics Are Covariances, a unified model of risk and return. Popular, won the Pharma DFA Award at the Journal of Financial Economics. Invented a new technique, the instrumented PCA version, which is PCA++, in the sense that it allows to utilize covariates to influence how it's compressed. So if you want to use PCA to learn factors, now you can also make the factors that you learn conditional on the covariate information that you have. I'm not going to go in detail on this because this is not really deep learning, and also because they publish autoencoders, autoencoder asset pricing models, which is basically the same, but it uses deep learning. So instead of PCA, it uses autoencoders, and it uses a neural network to enforce or to, learn or take into account the asset characteristics. So an autoencoder is a little bit like PCA in that it compresses data. The way it works is simply it's a neural network that is trained to reproduce. It's like an odd model where the input is the same as the output. What's interesting is what happens in between. So it's really like a neural network that's like a funnel, where typically it becomes smaller and then it becomes wider again. So say you have a vector that goes in that has 100 units. Maybe it's an image, right? 10 by 10 pixels. And you have that go in, and then in the middle you only have 10 units. So instead of 100, you go down to 10, and then maybe with 2 or 3 layers in between. What's interesting is what are the values of 10 units, and what is their output? Right? Because you can always grab the output at any level of your network. That is your compressed image in that case, if you use images. And so it's a compression algorithm that allows you to learn non-linear compression. That's an autoencoder. So they combine this and use on the one side an autoencoder to learn factors from data. So rather than use pre-formalized specified factors like the Farmer French and others, they learn the factors from the data. They learn conditional beta, so they learn conditional exposures to the factors. So the formula you see there, but the image probably will be more telling. So the next slide.
It's a form of reverse engineering.
Yeah, exactly.
Yeah.
Exactly. The idea is we do know from experience that there seems to be something like factors that influences asset returns, and there seems to be something like exposure to these factors. But we really don't know what these factors are. And people come up with all sorts of ideas, and these ideas are usually predicated on the data that you have available. Right? I mean, you may even come up with concepts, but ultimately you're stuck with the data that you have. So you can say, okay, now I have a variable that measures like how profitable the firm is. So maybe that's a factor that's tested, but then maybe it's really something else, in reality. So these models, they don't. This model is able to take all this information as input. So it takes all the asset characteristics. So it's similar in the inputs to what we just saw, in that it takes, a large number of the typical aspects of assets, that you would put into such a factor model, and then extract from those a small number of information pieces, different variables, that together with exposures that are also learned, based on what the assets look like, so what kind of characteristics are, to explain what the asset returns ultimately look like in the data. And that model actually performs pretty well. So the ability to learn the factors from the data and to also learn how these exposures behave improves the ability to explain returns and then also to predict returns quite a bit above what we've seen before.
And when you say factors, you're talking about momentum, quality.
So that's the familiar factors when you're a researcher and you think about something and you tie it to the data that you have. These are latent factors where concept of factors, but who cares what they're called as long as they work, right? So it's some variable that assumes some value at some period of time. It fulfills the same function as momentum, closer to the concept of a factor. And it goes back to APT. Ross portfolio pricing had this idea that there are these latent factors. Let's learn them. And there are applications that use linear models, like PCA, like Millen mentioned. Yeah, exactly.
Abstract factor.
Yeah.
So momentum, you've got 600.
We're trying.
How does that comport to this model right here?
So we do a lot of bagging and boosting and and those sorts of things as well. But primarily we just run ensembles and we finally get very compelling answers. We got some stuff that's up like 48-50% this year. So actually it's really about how you kind of combine the factors. That's our philosophy, and it's not just It's both, do you have a better definition of the factor, which is why it helps to have the whole zoo, right? So you can hopefully find the better ones.
Or is it just more granular?
Well, but it's both, right? So if you're more granular and you got a larger collection, then hopefully you're covering all the bases. But then the second part is, okay, now that I've got so many definitions of value or momentum or quality or whatever, can I find a better representation?
Yeah, so there's a term in machine learning called representation learning. And neural networks are really good at that, where the idea is that you have some input data and you want to predict something. And sometimes the input, the form that they come into the model, they are okay, but they're not great. And you could maybe transform them into something else, something new that makes the task much easier to perform. And you've probably seen these convolutional neural network stories, they're like these, where they learn these hierarchies, where you have like an image that goes in, and then the neural networks at different levels learns kind of different aspects of how to recognize an object. And it's literally a little bit like these old feature extractors that people used to design, where, well, to recognize a face, you want to know what a corner is and what a line is, and then how you can combine, etc. And the model learns that by itself, these feature maps. So that's what neural networks are really good at. So these factors are a little similar in that they are assumed to be latent, so they exist somewhere there, but we can't observe them. And the model is able to extract them in a data-driven way. The benefit of doing this, which involves data compression, is that you have in the end fewer parameters. The more parameters you have, the more accurate it can be, sure, but you might also be more wrong in many cases because you have a lot of noise in the input. So the more parameters you have, the more the output swing all over the place. You have more variance in the output, and you don't necessarily want that. So these are ways to be more precise, by making more and better use of information, by learning better representation. That's a characteristic that allows you to price the assets better. So that's that, and that was fairly novel, and in the sense that it's kind of interesting if you're familiar with, if you look at recommendation systems, they actually look similar. You often have recommendation systems where you have information about users coming in. On one hand, you have information coming in about user attributes. On the other side, you have information coming in about user transactions. Networks to extract certain information, and then to matrix score for a specific recommendation and the like. So structurally, there are actually some parallels between the models that have been used in other domains that are sort of now finding their way into finance, and they happen to be compatible with the theory.
If you look at the recommenders CNN, right? You look at the feed-forward portion. Right? The feed-forward portion effectively means that it's almost like a momentum factor. Right?
Sorry, can you?
I wonder if you're trying to use the CNN system approach, where there's no feed-forward. Feed-forward is effectively like a factor momentum.
Yeah. Certainly use, I'm not sure I understand, instead of a feed-forward network, you could maybe use different ways how you could extract from asset characteristics some prediction. I mean, this is the simplest possible implementation, right? So you almost see in the way these papers are implemented that also the research, they literally just become with what's out there, So I think we actually will today. So that's one example. Let's move on to the next slide to see some of the results, actually. So in this case, here you again have kind of the, this is again the Sharpe ratio, so monthly Sharpes annualized. So annualized Sharpes for, again, a strategy that, trades on the bottom and top and bottom deciles based takes the difference in returns, and this is an improvement over with this kitchen sink approach, right? So we see like this model is getting a little better. It also improves over the linear version, at least in some cases. We'll see with the criticism later again that in some linear version actually seems to be better, but that's for later. We have, which is new, that rather than using kind of an unstructured approach where we build a big model, try to throw everything at it, by actually being sort of more conscientious on how we design it and impose sort of more constraints that are borrowed from theory, we actually get also better performance. So that's encouraging, right? So that's one model. question. And this actually, so this is in the book. So in the book, I use, I have to sidestep the data issues. So we're downloading data finance, which means the input is not that great, but it's free. So, but the code is there. So the idea is if you have your own data, because you happen to work at an institution that makes it available, then of course you can build what you just saw yourself. Now, questions, can we do? Yes, we can, and we'll do. So, example on the next slide is about an example that uses generative adversarial networks alongside some of the. So it is a paper that's relatively recently published, was published, I think. So that focuses on stochastic discount, no arbitrage conditions, and uses the method of moments to estimate the stochastic discount factor. And that's kind of a very novel approach in some respects. And it gets lucky because it gets to use the term generative adversarial network, extremely hip in deep learning. And they actually found a paper that justifies using a minimax adversarial approach to estimate moments that happens to work in practice. So this model is way more complex, and it sort of follows the footsteps of what you see in general deep learning research, where the models just get in what they use. And this actually uses 3 different feed-forward networks, uses 2 recurrent neural networks, and the generative adversarial network, some of these networks. And so it estimates the stochastic discount factor, moment constraint. It also constructs test assets, so assets that the model actually uses to price to learn its pricing model, and it also comes with a way to condense macroeconomic information. So it uses like 170 macro variables. It comes up with representation learning again and embed and make more efficient use of that information. Again, it's probably better. So let's look at the next slide, where I talk briefly about what generative adversarial networks are. So,
but we need to switch. This one is going to die.
oh yeah, of course.
Very quick, just 5 minutes.
No, I'm here, so I'm
Have another sip. So what we're doing, just so people understand, we're running a parallel online, and that forum dies at 7:30. We're booting up another event. So those people don't get picked up.
What probably means I went way over time. I'll be able to stop here.
No rush, we're here.
Yeah, I'll check.
Yes, the prior slide. So you said the equivalent statement to the fact that the expected value of that factor times the return is 0.
Mm-hmm.
So the second of those 2 things, that's what you're trying to estimate, basically. You're trying to estimate the realized return over the next period, right? So to understand, so then, what does that mean? Condition that the expected value of the product is 0. What does that mean economically, that condition? Because you have an equivalence between that expected value being 0 and the other expression involving the covariances, right?
Yes.
The prior, I think it was the prior slide.
Yeah.
Just by itself.
Can we just go back one slide here?
Just by itself, that's the thing on the left. What does that mean economically? That you have the realized return, which you don't know. What's going to happen? You don't know until.
This is the idea is that there exists a stochastic. We look at different states of nature in the future, and they also are in the future. We are able, with a random variable, so this m here is a random variable that assumes different values in different states of nature,
Right.
that across assets is going to discount
Yeah,
The,
I'm typing him the new link.
the future value
Right.
to the current price.